Good morning. I teach 8 a.m. classes to undergraduate students, so I can be pretty lively. And especially with a topic like soil, I try to be extra lively because I find it to be very exciting, but I know it can be a little dry sometimes, but hopefully not too dry, which we'll talk about. So I am a watershed scientist, but part of my training is in soil nutrient cycling. And so I have done a fair bit of research on soil carbon and nitrogen cycling and looking specifically at physical soil properties and how those two things interact and affect one another. I have not been a pure academic. After every major degree, I've taken a break so that I could get my boots on the ground. I come from coal country mixed with Florida beach. I am hard to keep in the office. And more than that, one of my big goals in my career, I have come to learn, is to help bridge the gap between science and on-the-ground management. Because while we do have recommendations in place, sometimes it's not feasible or we see something different happening on our own properties. And so hopefully this can shed a little bit of light to some of that, with soil being the foundation. So soil, let's go ahead and define what that is. It is a dynamic material made up of fine particles like clay, organic material, and mineral fragments. And those mineral fragments are typically coming from eroded rock from the region, right? And that is going to play an important role on the different cations and micronutrients available in that soil. The difference between dirt and soil is soil can sustain life. Right? So what you sweep up on the floor at home is not soil. You can't plant a seed in it and grow it, right? That's dirt. And I make sure that I drive this home with all of my kiddos, from K all the way through graduate.
You may have already said this. Can everyone hear you?
Oh, can you hear me okay? Okay, great. Yeah, very good. So soil can sustain life. Okay, and that is how we view soil health in a lot of ways, which we'll talk about. And this is really important because soil is the foundation for all terrestrial life. If you strip the soil away, it doesn't matter how much rain or solar radiation you get from the sun, we don't have life because the plants that are the base of the food chain have to have healthy soils to grow in. Okay? So when we talk about soil health, a lot of the times we're talking about the soil's ability to support that life. And there are different measures of soil health and soil health indicators that we can look at and talk about, and that are kind of worked into the soil test reports that you get. But before we get to soil health, and what I do with my students is I make sure that they understand basic soil properties that are not explicitly stated or described on those soil tests. And unless you've taken a soil course, you might not think about these soil properties in their basic terms. And so I'm going to just introduce some basic physical, chemical, and biological properties of soil that we use as the foundation to understand soil health and then build upon that. And then I'm going to end by looking at some examples of management and how we might treat those or receive recommendations for feedback on the soil tests and measures of soil health and what that actually means in the foundational structures of the soil profile. So this is a big, long list. I'm not going over all of them. But this is our basic soil properties. And in order to even identify a soil, you've got to know things like color, texture, structure, porosity, chemistry. We've got things like pH and a little bit of that biology worked in. But what I'm going to do is talk about a few of these and very simply describe them, kind of textbook form. And I'm going to pick the ones that are most relevant for grazing systems. So soil color. Anybody can do a basic assessment of their soil if they understand some things about the color. Super easy. We can walk outside with a shovel, dig a hole, and start to interpret some things about that soil, right? And so these are going to be tools that you can even take home without ever even getting that soil test back, okay? So around here in East Tennessee, we have a lot of red, yellow, and orange soils. And everybody knows where those colors come from? Sorry, I do the Socratic thing. I'm sorry, I'm in my teaching mode. But red is oxidized iron, right? And that yellow is oxidized aluminum. So some of those cations that we look at on a soil nutrient test. And then, of course, if you mix yellow and red, you get kind of an orange color, right? Does anybody have a low-lying area on their property with standing water every once in a while? If you dug down into that soil, if that water stands long enough, you might see something that looks like this. Iron and aluminum are only red and yellow when they're oxidized, when there's oxygen available. But if you have standing water for long periods, you have a lack of oxygen and they become reduced. And they change to this lovely gray color. And so if you dig down and you see what we call a mottled soil color, you can determine that that area is likely to be an intermittent wetland. And just with that alone, you can start to think about how you manage it and what seed to sow there or what seed not to sow there. Because this is an indicator that you have high water table significant parts of the year. Now, of course, this is the color that we all want to see, and that's that nice rich brown, right? That is coming from carbon in the organic matter. Anybody drink coffee or tea? That nice dark color, right? That carbon is what gives us those dark colors, and it's the same in soil. When you have rich organic matter in soils like ours that are otherwise kind of a red or yellow, it will start to change color, and it is basically the presence of that carbon in the soil giving it that nice rich brown color. And so if you dig into the soil around here, we like to see a little bit of layer of brown because that's not always very common depending on the situation here, right? Soil color, super easy and cheap. Soil texture, sand, silt, and clay. Have you heard these terms before? Yes. The difference between them is size. So like I said, when we're defining soil, we have mineral fragments. And those mineral fragments get eroded and reduced in size over time. And the longer they get worked over, the smaller they get. Sand is basically just a size fraction of particles, okay? So if you have one little piece of soil particle, and it's between 0.05 and 2 millimeters in size, it's sand, okay? It can come from just about any source, it's sand. Now, if sand were a basketball, silt would be like a baseball or a tennis ball. Both are relatively round, but one is bigger than the other. Once you get down to clay, you're getting into fine particles, and there's something about clay that gives it its special properties that make us slip on it when it's wet out, and that's that they're not round particles, but they're plate-like. And so when they stack on one another, it's easy to slip, kind of like when you're hiking in the fall on wet leaves on the trail or something, right? It kind of comes out from underneath you. So that's how they're oriented. Now, soil texture is basically what ratio of each of these size classes make up the soil. And so if you have 70% clay, it's a clay, right? If you have relatively equal mixture of all three, sand, silt, and clay, we have a loam. If you have a little more clay than this, it's a clay loam. A little more sand, it's a sandy loam, right? And so this is how we get these determinations. And this is really important because the size of the particles and the shape of the particles is going to determine how those particles are positioned next to one another. And that's where you get soil structure. It's the orientation of these little pieces. How do they fit together? And this is really important because this is going to determine the air spaces in between the pieces. How many air spaces do you have? How big are they? Do they connect? That's super important because you have to have some space between the particles, and they have to connect for roots, water, and other life to move in between them, right? If you have no space between the particles, it's like trying to move through a wall. You can't do it, okay? And so we can look at soil structure, and what we would love to have on our farms is this nice crummy or granular structure, right? When you pick it up, it kind of goes through your fingers but kind of holds itself together a little bit at the same time. It's friable, right? It moves. But I think a lot of times when we dig down, especially in East Tennessee with a lot of clay soil, we have platy structure. And it's when those clay pieces are stacked on top of one another and there's not enough other particles or organic material or root masses to break it up and add those air spaces in between. I told you this was going to be really exciting, right? Okay, so if you have good pore space between the particles, water can move through. So different soil structures are going to dictate how water moves into and through that soil. So here's that crummy, funnily enough, the crummy stuff is what we want. A little ironic, right? So the crummy soil or the granular soil really has the pore space to allow water to infiltrate and then move through that soil column. And that's really important because we want water to get in, but we don't want it to stick around. We don't want those gray soils where we're trying to grow things, right? And if we have more clay and more compacted clay, you can see that it's quite a lot more for the water to work through that. Okay? And so we don't want this, we want this. And this is determined by those physical structures and how they're oriented. And a lot goes into that. So, soil porosity, is water making it in? And do we have soil solution? Okay, so water can make it in, but it might not stick around. Has anyone ever done kind of a sandy thing with kids or gone to the beach? Water just flows right through it and out. It doesn't stick around. So what holds things together is the combination of those soil particles and things like organic material that's kind of sticky. And so it allows for movement, it allows for space, but it also kind of holds things together. And organic material is spongy. It soaks up water and it holds on to it. And it can release it slowly over time, making water available to transfer nutrients. And this is why this is so important. You can have nutrients in the soil that could support productivity in your fields or croplands, but if you don't have the soil structure to allow that water to move into the soil and be retained by it, you don't have the medium for those nutrients to come from their source and make their way over to be in contact with the root hairs. Okay? And then, of course, this is a fickle thing too, right? Because plants and microbes can only use the water that's available. What does that mean? At some point, it's too dry. There's just not enough water to maintain that connectivity. And so the nutrients might be in solution here, but it might not make it all the way over to the roots. Okay? And so in very dry conditions, that water is not available for plant use. So we want to get past what we call the wilting point. That threshold where water does create the connectivity and roots can access those nutrients, that's a soil moisture level that we call the wilting point, because below that, the plants wilt. Makes sense, right? Now, we don't want too much water either, because we want to make sure that there's enough oxygen in the system to support aerobic processes, breathing, just like us, right? We need oxygen. Plants and microbes, they need oxygen. The other thing that we're going to be talking about today is when you get to this point, so much water can be held in the soil without being lost. Water kind of sticks to itself and other things, right? But if you get too much water, gravity will start to pull the water out of the soil column. And that's when you start to get runoff, and that's when you start to get leaching of nutrients and fertilizer. We're going to talk about why that happens in a minute. That point in your soil profile is called field capacity. That's when the soil is at capacity. If I get any more water, I'm just going to let it go. It's just going to run off. It's going to go out, and it's going to take whatever it has with it. So soil moisture needs to live here, but it can't unless you have the right soil components and the right soil structure. Make sense? So far, all building. Is this new or review? A little bit of both? Okay, that's great. These are the mechanisms, right? The nuts and bolts. Now, if you have enough water for plants to access nutrients available, we have a measure. There's this property of soil called the cation exchange capacity. Clay, an organic material, has a negative charge. And so those micronutrients that we get reports on, like sodium, magnesium, potassium, calcium, they are positively charged. And that's why they hang around in the soil. They adhere and they stick to the clay particles and organic material. And so when there's enough water in the soil for the roots to access it, they can come off in solution, come in contact with the roots, and the roots get those nutrients. Okay? So you want to have a good amount of clay is actually a good thing, but you don't want so much that it gets compacted. And so organic material is really good because it makes it a little fluffier, but it still holds on to those cations, right? And so this is a really important chemical feature of the soil, but it is reliant on the physical structure of the soil. Okay. pH. We all get this one, yes? This is an easy one. This is our pH scale. This is neutral. If we move this way, things are more acidic. Acidity in soil is based on the number of hydrogen ions. The alkalinity of the soil is based on the number of, anybody remember? Right, yep, say it loud. Hydroxide, yeah, you got it. OH, hydroxide, right? And so we're going to have a look at this in a bit. But for now, most plants like to live somewhere between like 5.8 and about 6.5 in this part of the world because we have a slightly acidic environment. In fact, our own bodies prefer a slightly acidic environment. Most organisms do. And so getting the pH right is really important. So when we have acidic soils and maybe we have something that needs to be a little more basic, we have management for that. But we don't want to over-manage for that because we don't want to go overcorrect and get to maybe a pH of 8 because that's not good for the plants. That's outside of their range. We're going to talk more about this in a minute when we talk about our management examples. Okay, soil biology. Now, this is important. It's an important part. You need to have the right soil structure to support biology profiles within the soil column itself. So if you don't have loose friable soil, you can't have moles and worms, and you can't have good root structures and things like that. And if you don't have good root structures and organic matter, and you don't have things moving those materials all around, then you don't probably have very good microbial communities. And if you don't have good microbial communities, they're not breaking down the organic matter to release those nutrients, right? And so biology plays a really big role in soil health and quality, but a lot of things kind of have to work up and stack up to support that biology in the first place, okay? So from here, we can kind of start to transition to talking about soil health. So these are basic soil properties, and you have to have the right properties in place to support healthy soils. And in fact, that's how we define soil health. It refers to the biological, chemical, and physical features of the soil as they are essential to long-term, sustainable agricultural productivity. And this is a commonly accepted definition of soil health. When we look at things from an ecological point of view or conservation point of view, I don't see many soil health studies. Soil health studies are primarily focused on systems where we are producing, croplands, farmlands, etc. And so this is something specific to maintaining and sustaining the production of food, fuel, and fiber. Okay? Now that's not to say these things don't play a role in environmental management and conservation, but it's not the meat of the conversation like it is in agriculture. So all of those soil properties aside, I'm going to guess that you don't really get those on your soil report, right? No, not really. Even though those are the driving factors to what the soil health can or cannot be. So what we get typically are soil health indicators. Bulk density. How many particles are stuffed into the volume of space that you sampled? This is an indicator of compaction. It's an indicator of soil structure. Right? Water infiltration rate is an indicator of soil structure. Porosity, right? Soil moisture. pH, that one's straightforward. That's a gimme. Cation exchange capacity. Now, you could have the clay, but maybe not the organic. You could have the clay and organic material. You could have the nutrients there. The potential's there, but maybe it's been compacted. Maybe there's not enough water. Maybe there's too much water. It's not really telling you what the problem is. And so sometimes what happens is we get management recommendations where we're treating a symptom, but we don't know the underlying cause of why we're getting those results. Okay? So, soil organic matter is a very meaningful soil health indicator. If you know how much soil organic matter is in your soil, it's going to tell you a lot of things. What's the biological input? How much life is it supporting for that dead matter to be there? Is it being incorporated into the soil? That tells you things about soil structure, porosity, cation exchange capacity. This is a very good one, and this is an easy one to check off on the soil test at UT. And this is the one I see least checked off on the soil test at UT. And in fact, I've had clients who have said, oh, well, I was advised just to get the pH and nutrient test, and I was told that the soil organic matter didn't really mean anything, so I never get it. And in my opinion, that is probably the most valuable piece of information on that test. Okay? Now, when you get soil organic matter results back, soil carbon is about 50% of that value. So if your soil organic matter is 3%, then you've got about 1.5% carbon in the soil. And 3% organic matter around here is pretty good. Okay. Okay. Bulk density looks like this. You can see why this matters. If you have a high bulk density, if you have a tight soil structure, you are not getting rooting depth. There's just not enough space for those roots to take hold, to get lower. And this can be a cause of nutrient deficiencies, because you could have the nutrient availability here, but the roots aren't able to access it because they're just not able to go far enough. You could also have more water storage at these deeper depths, but the roots can't get down there, or the water can't get down there because it's so compact and it dries up, it evaporates off, or it runs off and takes your soil with it. This is soil aggregate stability, and this is a really nice measure of soil structure. So you can see on the left, you've got soil that is a little brown, organic matter is in there probably, and it's kind of sticking together. It's holding together a little bit. And we put it to a test. We dunk it in water a few times. It's super simple. I could come to your farm, I could teach you how to do this in like 20 minutes. You dunk it in water and see if it holds. And if it does, you have good soil aggregate stability, meaning that when you have rain, it's less likely that it's going to compact. It's more likely you have good root structure, and it's more likely you have good exchange of nutrients. In contrast, you have something that doesn't have good soil aggregate stability. So you can imagine that soil that gets wet and water is moving down, pretend that this is lower in the soil profile. All these fine particles end up moving down as far as they can go, and then they all get deposited. And if that's clay, it creates an infamous clay pan. Right? Has anyone ever hit basically a clay pan when they start digging? Yeah. This is part of the reason that happens, especially in tilled fields, because you are creating a little bit of aeration in those top inches, and you get some water infiltration, it appears, and then it kind of hits a stop, and it will collect at a lower depth, and then that is where you start to hit this threshold where you have higher bulk density and lower water infiltration rate. And it's because of this process right here, because you lack that organic matter in those top few inches. Okay. Soil microbial activity. I never see this on a soil test. I have talked to so many people who have worked in soil labs, and I have done this work on like 2 continents and in 3 or 4 countries now. And this is by far and away one of the most informative pieces of soil health that I think exist out there. Soil microbes, like us, they breathe. They breathe in oxygen, and they exhale carbon dioxide. And I don't know about you, but when I'm hanging out on the couch, when I get the chance, because I have 2 small children, I am breathing a little less rough and putting out less CO2. But when I start hiking up a hill, right, I'm putting out CO2. Microbes do the same thing. When they are more active, they are respiring more. And that means that if you measure that, you can measure the change of carbon dioxide. You can measure their rate of respiration. And a higher rate of respiration means that they are active, they are turning over, they're breaking down organic material and releasing those nutrients for your plants. So this is a really nice measure of soil health. Okay. Now, connecting the properties and the health. I've already started doing this. If you dig into your soil on your property, you've got an indicator of organic matter, how much, a lot, a little, maybe none, somewhere in between. If you see that nice brown color, you know you've got something good going on. But if basically you've got maybe just some litter on top and you're going straight down into that red and orange, maybe we want to think about building organic matter, right? Soil texture and soil structure. These things dictate soil porosity. They directly affect bulk density, soil water infiltration, soil water holding capacity. And soil water holding capacity is directly affecting how many nutrients or what nutrients your plants can access. So you could have a good nutrient base and your plants just are not accessing them. So maybe this indicates that we got to think about management differently from just putting more nutrients on, right? But that's situational, of course. Now, 1, 2, 3 different things here could teach you how to do on your own property, on your own, in an hour. And you can measure this in situ and track basically the evolution of your soil without ever having to send off for a test. And that's kind of nice, right? It's cheaper, and then you start to become more familiar with your soil and how it's responding to your management. Because every site is different, right? Okay. So changes or disturbances to any of these soil properties directly impact soil health. Let's talk about some examples. I have a feeling you might pick up a little with these. Okay. How are we doing? Sometimes with students, after that kind of material, I'm like, do you need a stretch? Do we need like a yoga session? Okay. I'm going to talk about 3 examples of management relevant to grazing. We're going to talk about soil properties, and we're going to talk a little bit about how this could affect your bottom line, okay? Economically. Grazing management, I'm talking about stocking rate, rotation, fertilizer application, and lime application, okay? Grazing management. It's not the cow, it's the how. Animals can be really beneficial to our landscapes. Right now I've got a little homestead. It was in corn soy rotation, and we're using the small ruminants, despite what others may say, to improve the landscape. Although I'm sure there are more intelligent animals out there than sheep, I'll give you that. But how many animals? Are you overstocked or understocked? If you're overstocked, can you look at mob grazing? But that requires more management, intentional management, and really watching your forage. So the difference between continuous grazing, consistent access to the same space, typically with more animals per acre than should be on that space, is something that is very common. We have seen more of a shift to rotational grazing management where you break your property up into smaller paddocks and you're moving those animals from one paddock to another, allowing for rest and recovery. And there are many benefits to this for forage and animals, and I'm going to let our other speakers speak to that. But what I'm going to talk about is the impacts on the soil. The most obvious one is if you don't have plants, you have bare soil exposed. And if those animals are in the same place all the time, there is consistent, consecutive hoof action with very heavy animals, and even some of the lighter ones, and you get mechanical compaction. Literally just compacting, like if you're out there just tamping it, right? Now, that compaction is going to affect a lot of the soil properties that we just talked about, right? So, and in this scenario, you've taken away the organic matter input. Well, not you, but someone who's managing that, right? So the organic matter input has been taken away. And this is going to significantly alter the function of that soil due to the change in soil structure. So grazing management soil health indicators may not then need to look so much at the nutrients, but at some of these other aspects of soil properties. And it's not to say that you can't have that sacrifice paddock in the winter, because I certainly do. Maybe rotate it in the winters to one space or another to feed out the hay when you need to. But how do I know that that sacrifice period in the winter is really impacting the soil in a negative way? Well, let's look at what soil health indicators you would focus on. You can focus on bulk density. You can do that at home. You can directly measure the level of compaction if you know how to do it properly. Soil water infiltration rate, you can do this at home. You can take PVC pipe, know the diameter, know how much water you put in, and time it. And you can compare from one season to another. Is the same amount of water getting in? Is it improving? Is it getting worse? How do I need to change my management to make sure that I'm maintaining that soil structure so that water's getting in and moving through? Soil aggregate stability, you can do this at home, right? You can get those water, you can take your soil sample and you can dunk it and then see if it falls apart or holds together. I think maybe I need to build some more organic matter to hold that soil together a little bit more or something like that. So these are health indicators that we would focus on that you can do at home without relying on a nutrient-based management recommendation. Now, this is the one that you would probably send out to the testing facility, but these are going to kind of indicate already if there's been a significant change in organic matter, right? So they kind of all build on one another. Make sense? Interesting? Would you be interested in learning how to do those things? Okay, that's good. I'll take it. All right. So here is just breaking it down and putting the visuals to it. Compaction and low organic matter content result in that soil structure. There's your soil aggregate stability, water infiltration rate. Here's that ring, and it's a super easy. Once you know how to do it, the math is really easy, right? And you can just kind of have the equation, and you can kind of figure out, is it higher or lower, right? It is changing the nutrient availability. Here again, you could have a decent amount, at least of those micronutrients, but your plants just can't access them. And even when you take your soil sample, you could have them at lower depths, but you might not be representing that part of the soil profile, and your roots aren't getting down to those depths because the soil structure has changed and is not allowing, it's restricting that root growth. And so there you go. You just don't have the exchange capacity. Okay. Now, fertilizer application. This is a fun one. First of all, I am not anti-fertilizer. I just want to make sure that that's clear. I think that it has a place, and I think it has an important place. I am pro-optimizing fertilizer application and not over-fertilizing. Okay? And there are reasons for this. The recommended rates for nitrogen fertilizer, on average, is about 90 to 120 pounds per acre per year. And that could be distributed throughout the year. In some cases it is, in some cases it isn't. These recommendation rates are not designed for your specific farm. When you get this recommendation from the testing center, it is usually based on charts of what crops are you growing in general management, but your specific farm has its own things going on. And if you notice, on your nutrient reports, they don't give you how much nitrate is there. Have you ever noticed that? They don't test how much nitrate is there. And that's because nitrate variation changes, nitrate concentration changes very, very rapidly and greatly throughout the growing season. Nitrate is a product of decomposing organic matter. And so coming out of the winter and spring, microbes are kind of cold. They're not doing much. And then when it warms up, they become more active. They start breaking down organic material, say from cover crops or something else that's been left there, and they start to release that nitrogen in the soil. And you get an inherent boost from that. And that's why cover cropping can be beneficial in that way. And there are other benefits as well. But it varies. And I've measured this directly in agricultural soils with long-term management practices, like over 30 years of the same management practices and comparing them. It is going to vary. What this is based on is industrial agriculture. A lot of what we see is based on large-scale farm research, which is fine, and they want maximum yield because those businesses need that yield for their bottom line, or whatever the case, right? That's kind of how industries work, right? And they can kind of afford the cost of doing this because of other things that they've done by mechanizing and things like that. But for a small farm, this is being well managed, probably too much. So there's another thing that happens, and that's timing of spreading the fertilizer. I've got no qualms with this. When cool season grasses start to come on, put that fertilizer out. Yeah. They want it, and when it's really beneficial is when the plants are going from little to big. Plants take up nitrogen during vegetative growth. When they first germinate, so if you have a crop field and you see those first little leaves come up, those are embryonic leaves. They house the nutrients for the plant until the first true leaves come on. And until the true leaves come on, those roots are not taking up much of the nutrients in the soil. And one thing that I see is kind of people putting the fertilizer out too early. They get germination, and they'll put the fertilizer out, but the plants don't have true leaves, and they're not actively taking it up, or they're not in an active growth phase. So during the vegetative growth, you want to get that fertilizer out, and then once it starts to go to seed, the nitrogen uptake slows down again, okay? Because it is focusing on different things. It's focusing on other nutrients being put into the seed so that baby plant has everything it needs when it germinates next year. Okay? So the timing, this is great. This is a great guide. But here again, you know your land better than anybody else. You know where your plants are in their growth process better than everybody else. And so you can really start to tailor when you add that nitrogen to your system. Now, here are the typical forms of commercial fertilizer: anhydrous ammonia, urea, and urea ammonium nitrate, or UAN28, which is 28%, and UAN32, which is 32%, okay, in solution. Now, you don't really need to pay too much attention to these, except that they all have a neutral charge, just about. Okay? And nitrate, when it breaks off, has a negative charge. What charge does our soil have, primarily, that holds on to the nutrients? It's negative. So forms of nitrogen are not readily adhering to the clay and the organic compounds, to the soil colloids. That means that you've got to get that timing right in terms of soil moisture as well. You want to hit it where it's not too dry and certainly not too wet. If you've got a big rain coming, you might want to wait to let that moisture create the conditions for good nitrogen and other nutrient uptake so you don't lose your investment. About 65% of fertilizer is lost from the system because of timing and the chemistry. So, what happens? Let's say this is hanging out and it's dry, right? Or maybe it's at this point in the growing season and then a big rain comes. Well, there's not a lot of room for uptake. You're going to very quickly reach saturation, and you're going to very quickly lose water. And you're not going to have a lot of time, even if you're in vegetative growth, for the plants to actually take up that nitrogen source. And so if it's nitrate, it typically goes right out of the system because it's negatively charged and it's not adhering to the soil colloids. And in terms of the forms of urea and ammonium, you do have, with anhydrous ammonia, you do have some adherence to the colloids. And it sticks around longer. And it's been designed and engineered to do that, to address this exact issue. However, plants don't readily take up ammonium primarily. They can. They do to a bit. There's some work looking into it. But plants need nitrogen in the form of nitrates. And so that ammonium is in the soil, and it's good that it can have some residence time because we need some bacteria to transform it into nitrate so the plant can take it up. But if you don't have a good microbial community, those transformations aren't taking place. Right? So you have to have the soil structure and the soil health in place to optimize plant use of the fertilizer that you're putting out. And pair that with a little bit of timing, and you're good to go. Now, the excess for nitrogen that's hanging out that does not get washed away, when we have the transference, or when we have the reaction that transforms ammonium into nitrite, we lose hydrogen atoms. Hydrogen atoms get released into the environment. And what did they affect? pH, right? And remember that the more hydrogen ions you have, the more acidic your soil is going to be. This is why over-fertilizing results in soil acidification. Okay? This is the process. Now, with organic material, that's typically the background source of nitrogen. It's more stable. It's more protected because of those soil colloids. It gets worked at a little bit over time. And so you have a nice background. If you have good organic matter, you have a nice background, more consistent release of that nitrate. And it ebbs and flows naturally with temperature, moisture, and soil microbial activity. These inorganic forms and added forms of nitrogen are going to be more readily transformed, which is why it requires more applications when we're reliant mostly on these inputs. Okay? Now, loss of nitrogen from the soil. A farm budget is basically losing 65% of its investment if it's over-fertilizing. That's a lot. Now, I based the 10-acre application on the national average cost of fertilizer right now. I think it was UA in 28 or something like that, and it was $83. But I was informed this morning that you could expect to pay more on the order of $500 to $600 to $700 per ton. $620 a ton right now. So, 10-acre farm. I mean, I don't know if I want to do that math all right now, but right? I mean, you're not only putting 1 ton out, $620 a ton, $620 a ton, and we're talking about 100 tons. That's 6,000 times 10 acres. That's $60,000. That adds up. This budget is a lot for me because I'm poor, but on that scale, right, I can't even imagine. So you want to protect your investment. And when we're talking about grazing for profit, we want to think about reducing our inputs so that when we sell the product, there is greater margin for net profit. And this is one good way of doing that. And if you've managed your soils and you've got the right structure and you've got the right properties, you've got good soil health, you can reduce those inputs. Okay, not eliminate necessarily, but certainly you can reduce them. Okay, soil acidification also creates the need for liming. Loss from the nitrogen. The other thing that we have is an environmental effect. I don't know, I assume that everybody knows this, but I have a surprising number of young adults in my classes who don't know this, so I'll just throw it out there. Where does that 65% of our investment go? Well, it goes into the creeks, that goes into Tennessee River, that goes into the Mississippi River, and that goes out into the Gulf of Mexico at New Orleans. And that big flush of nitrogen causes algae blooms. And this has happened for decades to the point that where the estuary is, where the Mississippi opens into the Gulf, there has been so many algae blooms, it's blocked out all other life, and there's an anoxic zone. There's basically no life there now. And this is primarily attributed to fertilizer runoff from agricultural operations in the Mississippi floodplain. So these are large-scale effects, even beyond our own properties and bank accounts.
Is a lot of that residential?
No.
It's agricultural?
It's primarily agricultural. Yeah.
Farmers are wasted, not the urban people.
Yeah, I think it's something like of 115 million tons of fertilizer attributed to agricultural use. 75 million tons of that is making its way into the waterways. Yeah, that was the most recent. Okay. All right, so soil acidification creates the need for liming. Okay, so we can pay for the lime. It is just fine to use lime. Lime is actually pretty beneficial. On average, so lime can help fix some acidity. It can actually help with soil structure. It can help with porosity. It can help with a lot of things. So I don't have anything against using lime, especially where we have, maybe soils that need to be regenerated. However, if you find an operation that is consistently applying 90 to 100 pounds per acre, we find that those operations are having to lime their soils about every 3 to 6 or 7 years because of the acidification from the excess nitrogen. And so as a result, this is going to be a high use of this product. We know that we can reduce fertilizer inputs to below this threshold of about 80 to 90 pounds per acre, and that's where soil acidification occurs. Lime is an additional expense, and if you have good soil health, you don't have to do it for very long stretches, if at all, within most of a lifetime sometimes, if you have a sustainable system. So if you can reduce fertilizer rates, you don't have to eliminate them. You can still give your crops and your forages those boosts, but if you can reduce it down to like the 30 to 60 pound range, you're not going to deal with that soil acidification issue. And you can circumvent the need for that regular liming. You can do this by supplementing with nitrogen-fixing cover crops. I worked on a study where we found that hairy vetch alone put 30 to 60 pounds of nitrogen per acre per year into the soil. We did not put in any nitrogen fertilizer, and they hadn't for 30 years, and the yields were the same as tilled, no cover crop, and 100 pounds per acre per year. Same yield, higher return on the product. Oh, yeah, that's per acre. Per acre per year. Sorry, thanks, that's a typo. 30 to 60 pounds of nitrogen per acre per year. Thank you.
On those numbers specifically at the bottom, what amount of seed was put in the acre?
I think that the seeding rate was, for the nitrogen fixers, I think it's only like 5 to 10 pounds per acre or something like. It's not much, especially for like crimson clover and things like that. It's pretty low. Okay, I'm being told I don't have much time, so. But we're working in questions already, so. Okay, no, you're good. I'm fine with it. Okay, so there's another reason besides just getting rid of that cost to consider using this approach and reducing the lime. So if you have too much of a buildup of calcium, if you are liming every 5-6 years, calcium will build up in the soil. And calcium adheres really well to your soil colloids, your clay and organic particles. And it will displace, sometimes, other cations and micronutrients. And they can be lost, or they're not made available to the plants for uptake. And so you get a nutrient imbalance. And the other thing that can happen with lime that's really interesting is it affects the arrangement of soil particles. So if you have low calcium, you might have like weirdly stacked colloids or clay particles, and they might end up kind of wanting to be a little more compact. But if you have enough calcium, it creates a nice structure allowing for water to move through, even in more clay soils, But if you have too many, you create so much pore space that the water runs right out. And typically in these systems, they are going to be systems that are low organic matter input and high nitrogen use. And so you don't have the organic material to soak it up and hold that water in the profile. Okay? So, takeaways. Soil management practices directly impact soil health, and specifically, soil management practices alter soil properties. And it's these underlying soil properties that we need to be thinking about, because we can kind of fall into a trap of managing the symptoms. Sound familiar, healthcare system? Managing the symptoms rather than addressing the underlying issues, which are these basic soil properties that create soil health. Okay? And so preventing the issues is obviously the best way, but regenerative practices and sustainable grazing practices are key. And that's because they give us organic matter, they give that rooting depth, we're pulling things off, we're limiting compaction. We're doing all of those things to maintain the integrity of that soil structure. Now, my recommendations for soil tests, this is straight from the UT website. This is what is most often checked off. This is great, monitor it. That is perfectly fine. Please check this box. Just for your own sake. It might not change very much from one year to the other, but you may be surprised if you really, or we have found that folks who really shift to intensive regenerative, we see really good results in a few years, depending on the situation, especially integrating livestock. And then I always like to put out, we're not trying to manage for maximum outputs. We want to optimize our outputs. We want to optimize our operation and optimize our inputs so that we can create more margin for profit once we get to selling the product, right? Okay, so here are my future shepherdesses. Actually, they're kind of already doing it, but they're in training. I would be happy to take any questions. Yeah, absolutely. There are sources. You can look at UT Extension or other regional extension resources with. Oh, so the question was, where can you find resources that give you options for nitrogen-fixing cover crops and what the recommended seeding rates are? I would say that, you know, I do work on helping create those management plans, but I would also say you can look at extensions like Tennessee extensions, North Carolina extensions, Kentucky extensions with similar habitats to what your farm may be. And I would say that there is some live and learn. Certainly, like hairy vetch can gunk up machines if you do any kind of machine work. Clover seems to be really nice for livestock, but I'm going to let our forage specialists speak to that more. And then there are certain things, for instance, in the summer, partridge pea is a native. But I have a few clients where it just took over and it kind of outcompeted some of the other high quality kind of forage or grasses that they might have wanted. So I think there's a live and learn, and those are starting points, and then figure out what works on your place.
Less with these also works well.
Yes, thank you. Less with these is a fantastic one. Thank you.
I work with UTB and Forage, and I'll say that utb.com is where you can find all of the seeding rates and the extension stuff that will tell you all of
UT Beef and Forage, and that, yeah, that's an affiliate, basically part of the extension. Yes. Mm-hmm. I think 1, 2, yeah.
Is there any way to get your slides? I didn't bring it.
I would be happy to post a PDF of my slides on our website. Yes.
We are recording the presentation, so
Yes.
you'll be able to go back and watch it on YouTube.
Yes, yeah, we are recording the presentation. So
I was wondering the effectiveness of running chickens behind the cultivars as opposed to using a commercial fertilizer.
I love this. I love this. We are, part of my story is we want to have an integrated, and Greg, I'm going to steal this from you, but the FLIRD. I first heard that from you, and that's the flock and the herd, and that includes poultry, in my opinion. Poultry are a great addition to rotational grazing management and pasture systems. Not only can they help with pest control because they are eating those pest larvae off of the manure, but they're also offering manure that has a different kind of ratio of nitrogen, phosphorus, and other nutrients that is different from the ungulates, or not the ungulates, excuse me, the ruminants. Mm-hmm.
Question about the cat and exchange capacity. I heard someone say recently that he was referring to soil tests and kind of generalized about CDC and said, well, that's basically soil organic matter. And I understand that the CDC is affected by your chemistry, soil chemistry, as well as amount of, or how much clay you have, as well as how much carbon. Is it safe to say that like your CDC values would be, the range would be kind of predetermined by how much clay is in the soil, but then where in that range you can shift it would be based on how you were managing for your organic matter?
Yes, in this part of the world, I would say that that's a very good interpretation. And basically the question is CEC, the cation exchange capacity is a function of what are the components of the soil. As we know, clay allows for cation exchange capacity. We have clay, and so here if you have low cation exchange capacity, one thing you could look at is if you have low organic matter, increasing that organic matter can improve that cation exchange capacity. When you're doing that though, you are also probably managing for soil structure and porosity and soil water holding capacity. And all of those things are typically related and correlated. And so as you build organic matter, you're also affecting the soil structure. So there is a physical component of the soil that is also allowing for a higher exchange rate. So there's kind of the capacity, and then there's the actual exchange rate of those nutrients. Yeah. One more question. Yeah. Okay, so when you have compacted soils and maybe you have a pan, I have worked on really rugged sites that were non-agricultural but were construction and had not been well established for, 20, 25 years. They couldn't get anything to grow. Basically, I used a cover crop treatment for a year, and that would be the equivalent of basically picking out a section, letting it rest. And when I did that, I was using cover crops that had good rooting depth, high carbon and nitrogen plants like your grains, some grains. Nitrogen fixers, of course, but the key is to put in some tubers. So purple top turnip, radish, and daikon. They are tap roots, and they will break up that soil for you. They will do the work. And then when you kill the cover crop, that breaks down into new organic material and just becomes incorporated in the soil. No reason to till. In fact, it will kind of undo the process. You just let it decompose in place. And we've had very good results within 2 to 3 years. The vermicompost, any kind of compost is good, and I think the vermicompost falls into that category. But basically, yeah, with those casts, they add another kind of form of nutrient base to the, yeah. So like basically worm tea, yeah, absolutely. Yeah, any of those organic, carbon-rich, they're going to give you a boost, absolutely. And in some cases, we see some of those additives in place of some fraction of nitrogen fertilizer so that you can offset it and reduce the inorganic form of fertilizer. Mm-hmm. So I think I'm out of time. But thank you. I know soils, so yeah. Okay.